Hello and welcome to class time. I'm Nikisha Hardy.
And I am Tyrone Brown. We are your CSEC mathematics teachers for today, and we will be learning about the volume of compound solids. Let's begin.
Okay, so as Tyrone said, we'll be looking at volume of compound solids. So that means these are the objectives for the lesson. We'll be reviewing the formula for the volume of solids.
We'll be calculating the volume of solids.
And also calculate the volume of composite or compound solids. We'll be using that word interchangeably. So let's get into it. What is volume?
The volume of a solid is the amount of space inside the solid.
Okay, so let's consider this cylinder. Now, if we were to fill up the cylinder with water, the volume would be the amount of water the cylinder could hold, right?
Yes, definitely.
So here we're filling up the cylinder. Now, how do we measure volume?
We can measure volume in cubic centimeters.
Now, here is a cubic centimeter. Notice it is a cube which measures 1 centimeter in all directions. So, Tyrone, talk to us about uniform cross-section.
Okay, as you see here, the uniform cross-section of this shape is the region that is going to be uniform throughout. And it's a congruent shape formed by cutting through the object.
Okay, so if we slice through this cuboid in the same direction throughout, what we are seeing, the shape that is consistent, would be the cross-section, and in this case, a rectangle.
Yes, in this case, it would be a rectangle.
Okay. Is it possible that we could cut it in the other direction?
I'm thinking possibly, because I'm seeing 3 pairs of congruent faces.
Okay.
So I'm seeing top and bottom, I'm seeing left and right, and I'm seeing front and back.
Okay. So as long as we have a congruent shape that we can see when we cut through the solid, that shape is considered our cross-section area. So notice as we cut through this shape, the shape of the rectangle remains consistent. Now, if you should look at this cylinder, what do you think would be the cross-sectional area? What would be the shape for the cross-sectional area for this cylinder?
And as we were discussing before, the cross-sectional area would have been the congruent shapes. So I am seeing 2 faces, 2 circular faces.
Yes.
That could possibly be congruent. So I am thinking it's going to be a circular cross-section.
Yes, you're correct, a circle. Now, what about this?
Okay, in that case, I am seeing a right-angled triangle as the uniform cross-section.
Yes, you're correct. So a right-angled triangle would be the shape that would be maintained if we cut consistently throughout this solid. And here we have this shape.
Wow. This seems to be, I'm seeing a semicircle.
At the top?
At the top, and then I am seeing a rectangle.
At the bottom.
At the bottom.
Right. So this one has 2 cross-sectional area. And finally, this one?
I am seeing, if I cut throughout, I am seeing a pentagon as the uniform cross-section.
A pentagon, yes. So we have to bear in mind the uniform cross-section for the solid when we are going to be calculating volume. And you'll see how important that is as we go through the lesson. So let us just review how to calculate the volume of cuboids. So let us look at this cuboid here, which has a length of 10 centimeters, width of 3 centimeters, and a height of 4 centimeters. And we want to find the volume. It therefore means that we must first, before we can calculate the area of the cross-section, we need to identify the cross-section.
And I'm thinking in this case, as we had said before, there are 3 possible regions we could use as a uniform cross-section. But I think we'll stick with the one that it's currently resting on,
Yes.
which is currently measuring 3 by 10 centimeters.
Okay, so that would be our rectangle. So we must first calculate the area of this cross-section, and it's a uniform cross-section. So the length and width of this rectangle is 10 centimeters by 3 centimeters, and therefore the area of this cross-section would give us,
as we know, it is going to be a rectangle, so it's going to be 10 multiplied by 3, which is 30 squared centimeters.
You're awesome. So let us see how we're going to use this area of cross-section to calculate the volume of the cuboid. So that's our 30 centimeters, square centimeter area.
I am seeing something peculiar. That is just one layer.
One layer.
But on the other side, I'm seeing the dimension going up to as much as 4.
Right.
So I'm thinking we could possibly increase that up to
about 4.
Up to 4.
Up to 4. And that would give us our height. So that would be the height of the cuboid. So there are 4 layers, as you said, which would be the height. So now we use the area of the cross-section. And therefore, since we know the area of one layer of the cross-section, we can therefore find
the total volume, which
total
would have been
volume.
the 4 layers.
Right. So instead of, we could count up all the cubes that we're seeing here, or we could just simply multiply the area of the cross-section by 4. And that would give us 120 cubic centimeters. And that's how we write our volume, cubic centimeters.
A quick question, Nikisha. I realize that you're saying cubic centimeters and not centimeter cube. But that's what I hear a lot of people saying, centimeter cube. So why would it be cubic centimeters and not centimeter cube?
Remember when we just started out, we talk about the cubic centimeter cube that we had. Now, when we say centimeter cube, we're saying cube the centimeter.
Okay.
Just as if we were to say 4 squared or 4 to the 3rd power.
Okay.
And that is not what we want. That's not what we're doing. We're looking at how many cubic centimeters are able to fill.
So if I actually said 5 centimeter cube, that would be 5 times 5 times 5.
And that's not what we're doing.
Okay.
So the correct
okay.
thing to say is cubic centimeters.
I understand.
Good, clear. Now, let us consider so therefore from what we have done, we can formulate a general formula for calculating volume. And that would be the cross-sectional area times the height, because that's what we did just now to calculate the volume of the cuboid.
For the cuboid, yes.
Yes. So let's see if that continues.
And we'll see which other types of shape we can actually use this general formula for.
Yes. Now here we have a cylinder. And let's see, these are the dimensions. We have a diameter of 4 centimeters and it has a height of 6 centimeters, and we want to calculate the volume.
Okay. I'm seeing something peculiar, Nikisha. I'm seeing a uniform cross-section on this shape.
Right. And what is that?
And that uniform cross-section in this case would be a circle.
Yes. So based on our previous activity with the cuboid, we found, what would we be doing with the circle? How will the circle help us?
We can find the area of that circle to get the area of the cross-section and then multiply that value by the height.
Very good. So we therefore need to find the area of the circle. And if we know the formula for area of circle would be pi multiplied by radius square. Now notice in our example here, we are given the diameter. So in order for us to get the radius, what do we need to do?
I'm recalling something from class. teachers always tell us that the diameter is twice the radius. So I'm thinking the radius is going to be half of that 4 centimeters,
And
which is going to be 2 centimeters.
yes, and I'm sure teacher proved it to you.
Yes.
So we're going to be using 2 as our radius, and when we square 2 and multiply that by pi, we get an area of 12.56 squared centimeters. No, we're not done. That's just the area of the cross section. We need to find the area of the volume of the cylinder.
Okay.
So we're going to use the area of the cross section, and then
we're going to multiply that area of cross section by the height, and we are going to get.
So we're going to multiply
12.56 times 6.
And that should give us a volume of
75.36 cubic centimeters.
Awesome. So the general formula for the cylinder volume, pi r squared being the area of the cross section, the area of the circle, multiplied by the height. So let's look at a triangular prism. And as it says, a triangular prism.
Okay, again, I am seeing that same uniform cross section coming out.
Right.
Right?
In this case, a right triangle.
Yes.
Right. So the first thing we need to do is to identify the shape of the cross section, which is a triangle, the right triangle in this case, and then we would need to
find the area of that cross section.
Right, which formula would work for, seeing that it's a right triangle?
We can use half base times height.
Good.
In this case.
All right, so substituting those values in the formula for area of the right triangle would give us the area of 12.5 squared centimeters. And now that's just the area of the cross section. We need to find the volume. Using the cross section.
And we would go ahead and multiply that 12.5 multiplied by 8, and we'll get the total volume to be 100 cubic centimeters.
Great. So calculating volume of compound shape is fun, it's easy. We just need to find area of cross section multiplied by the height.
And so far we'd have been looking at some basic shapes that persons would have been using.
Yes.
Some cylinders, some triangular prisms, some cuboids.
And such. So let us look at this one. This is an interesting one. The cone. So we are going to compare the relationship between the cylinder and the cone.
Okay. I am seeing where they are sharing a circular region, but there's something particular with the cone. It is not a uniform cross-section throughout, because I am seeing at the top region there, they're the same.
Yes.
But as you go down, the cone seems to be reducing in the cross-section.
It's tapering off
Yes.
to an apex. Right. So in situations like this, in this situation, we have the diameters to be the same and the height to be the same. Now, calculating when you were in class, Tyrone, remind us of the experience that you had when you were comparing the relationship.
Well, I remember doing that experiment in class, and when we did the experiment with our teacher, we poured some liquid. She had some liquid, and we poured the liquid into the cone.
Yes.
And we used about 3 of those measurements and got that to fill the cylinder.
So basically, yes, I remember too. So it means that it took 3.
The volume of 3 cones
to fill
the cylinder.
To fill the cylinder.
Yes.
Okay. So seeing that it took 3 cones to fill the cylinder, how significant is that 3? Let's see how significant that 3 is in coming up with the volume, the formula for the volume of the cone. So seeing that it was 3 times, the cylinder is 3 times that of the cone, it would mean therefore what?
I'm thinking it would have been the opposite in terms of reciprocal. So it is going to be 1/3 the volume of the cylinder.
Yes, so the cone would be 1/3 the cylinder. Good. So we're going to see how that 1/3 come into play in calculating the volume of our cone. So it therefore means that the cross-section, the uniform cross-section, even though it's a circle, but it therefore means that we're going to find 1/3 of that cross-section.
Okay, and in this case, we are saying it doesn't have a uniform cross-section, but it does share the same area.
The diameter and the height.
The same diameter and the same height.
Yes. And that is how the 1/3 comes into play when we're calculating the volume of cones. You think there's any other interesting, you think this only applies to cones?
I think probably other shapes with an apex, but let us see.
Let us see. All right. So let's consider the pyramid and the rectangular prism.
I am seeing something similar in this situation. They have the same height, and the cross-section seems to be the same on the base.
On the base, yes.
On the base, both cross-sections seem to be the same.
And we notice that the pyramid, the square base pyramid, is tapering off just as our cone tapered off at an apex. So we can come to the conclusion that, or we did try it and we saw that it took three square base pyramid filled with water to fill the rectangular prism.
Yes.
So we can now generalize that this formula would apply to the square base pyramid as well.
And that is important, students, because this is a special relationship between the pyramids and the associated prisms.
Yes.
Right? So that's one of the things to remember. And it helps us to remember when we need to derive formulae.
Yes. So we can say that the formula for the volume of a pyramid is 1/3 the base area times the height. All right. Things have been going so interesting so far. So we have looked at quite a bit of solids and also formula. It's so many formulas to think about, so many formulas to work with. But if we should bear in mind that we're looking at the cross-section, the area of the cross-section, times the height, and that would give us the volume.
Okay, for the prisms.
For the prisms.
And then for the pyramid, it's going to be 1/3 of the base area times the height.
All right, so let us do a quick check and summarize. So notice for the cuboid, the volume would be...
The base area would have been length times breadth times the height would give us the volume.
And the cylinder?
The area of the cross-section would be pi r squared, and multiplied that by the height will give us the volume of the cylinder.
And our triangular prism?
This also has a uniform cross-section, so it's going to be half of the, it's the base area, which is half base times
height.
Half base times height multiplied by length. Yes.
No, and the cone.
This one does not have a uniform cross-section, so that is where the 1/3 starts to come in for those meeting at an apex.
All right. So this one I'm going to bring on the screen, we did not go through because that would take us the whole session, mostly. Yes. So we're just going to give this to you where we have the volume of the sphere, and we're going to talk about it a little later. You're going to see. So bear this in mind, the volume of the sphere being 4/3 multiplied by pi r cubed, right? So 4/3 multiplied by pi r cubed, and you may be thinking of some relationship as though we came up with the formula for the cone. But 4/3 pi r cubed for the sphere.
I'm thinking it's related because of the circular regions on the sphere, and that's why that pi is coming out.
Yes, definitely.
But as you said, it would take too long for us to actually prove and derive that for us now. So let us just look at.
All right, so now that we have looked at volume of the shape, solids, we're going to be looking at composite or compound solid. And based on the word, it is suggesting that makeup of more than one. Because as you see on the screen, this part here is made up of a...
I'm seeing a cone and a cylinder.
Yes, and the one over to the right.
That one is a little bit tricky. I'm seeing a half of the sphere,
half of the sphere, which is
which
called
is
a
called a hemisphere,
hemisphere, yes.
and a cylinder.
And at the bottom here we have,
I'm seeing another hemisphere,
yes.
a cylinder, and a cone.
All right, so that's our composite shape. They are made up of different parts. Now you have composite solids in the environment around us, and you'd be surprised at how important calculating the volume of these compound solids is to us in everyday life.
Yes, yes.
Take, for example, this hopper bin. This hopper bin is made up of a cylinder and two cones. And the shape of the top and the bottom is very important because that allows ease for the grains. They store grains in these containers, and based on the shape, having the cones, that allows for ease of flow of the grains out of the bin. And you notice cylinder and cones. So let us look at another example.
Whoa, that's a house.
Yes, right. It's made up of two basic shapes being put together.
Yes, and most persons would have known the rectangular prism.
Yes.
That portion of the house, but I don't think a lot of people visualize the triangular prism at the top.
Awesome.
Being the top of the house where the roof is.
Yes, and our contractors or builders have to be aware of these things in order for them to construct properly when they're doing their jobs. All right, so in summary, volume of compound solids. In order to find the volume of a composite solid, you need to identify the different parts that it is made up of.
This decomposition allows for working out of the volume of each part independently.
Yes, because we wouldn't be able to work them out all at once.
Yes.
So we'd have to know how to work out the volume of each part. And then after finding the volume of the different parts, we simply add or...
We can take the difference or subtract.
Right, of the parts. Okay? So let's look at an example.
We are going to take a quick break. When we'll be back with more mathematics.
Welcome back to class time. Let's pick up where we left off.
Okay, so Nikisha, so far we would have been looking at the basic shapes and the volume of those basic shapes, and now we'll continue to do a little bit of exploration into the volume of composite solids. So let us look at this example.
So we have, it says here, an aeronautical engineer designs a small component part made of copper that is to be used in the manufacture of an aircraft. The part consists of a cone, as we can see at the top, of a cylinder, as shown in the diagram below, and we're to find the volume for the part. And we're also to leave our answer in terms
of pi. Oh, okay. So as you said before, we are seeing where we can find the volume of that cone at the top.
Yes. And we know how to do that.
And we know how to do that because we would have gone through that before. So we would have to find that volume and then find the volume of the cylinder, and then we can work from there.
All right.
So let's begin. The volume of the cone. As we had discussed before, the volume of the cone is going to be 1/3 the base area times height. In this case, the base area is a circular region, so it's going to have pi r squared as its base. But we were given 8
for the diameter.
For the diameter.
Yes.
So how does that relate to the radius?
All right, remember that the radius is twice that of the diameter. So therefore, we need to get half of the diameter to substitute in our formula for the radius.
Oh, and I'm seeing that is where you have the 4.
That's how the 4
of 8.
Yes.
Okay, so once we go ahead and do that calculation, we will get 48 pi cubic centimeters as the volume of the cone.
And we're done with the cone.
Yes.
All right, so let's look at the cylinder, volume of the cylinder.
For volume of the cylinder, I am seeing that same cross-sectional region, that pi r squared, a circular region. So I'm thinking we're going to do the same thing there in terms of finding the area of that cross-sectional region.
And we're going to be using the same diameter as
the same diameter, yes.
So it therefore means that we'd substitute 4 for the radius again in our formula to find the volume of the cylinder, which would give us a volume of
96 pi cubic centimeters.
So we have found the volume of the cone and we have found the volume of the cylinder. Now what do we do with these two values?
And this is where it takes some analysis.
Yes.
Because looking at it, I am seeing where the volume is going to be combining the two figures together. So I'm thinking we're going to add those figures together.
Definitely.
So I'm thinking 48 pi cubic centimeters plus 96 pi cubic centimeters, which will give us a total volume of 144 pi cubic centimeters.
Right, and we leave our answer in pi as that was asked in the question for us to do. Okay, let's look at another example. Here we have a hemisphere, half of the sphere at the top, and a cylinder.
Okay, the shape below is composed of a solid metal cylinder capped with a solid metal hemisphere as shown. Find the volume of this shape, and they want us to give our answer in 2 significant figures.
Okay.
Okay, Nikisha. We know the volume of a sphere.
Of a sphere, yes, which is the volume of the hemisphere, as we had said before, was 4/3 pi r cubed.
But in this case, we don't have a sphere, we have a hemisphere.
Right.
So how will that affect our formula?
Okay, so the hemisphere, which is half of the sphere, would therefore mean we would have to divide by 2.
Yes.
The volume for the sphere to get the formula for our hemisphere.
And that gives us 2 divided by 3 pi r cubed.
Right.
Or 2/3 pi r cubed.
2/3 pi r cubed. Now, notice our diameter is 18, and we need to use radius.
So again, we're going to have to find the radius by dividing the diameter by 2, and that is going to be 9 for our radius.
And then we substitute those values in the formula, and that would give us a volume of 486 pi cubic centimeters for the hemisphere.
Yes. So next we would need to find the volume of the cylinder, and we're going to use the same radius because they are sharing the same cross-sectional area
Yes.
with that diameter of 18. So it is going to be pi times 9 squared times 10.
Awesome. And that would give us a volume of 810 pi cubic centimeters. Now to find the volume of the compound solid,
I'm thinking again, because those two regions are combined together, we're going to have to add those values.
now notice we have 1,296 pi cubic centimeters, but the question asks us to leave this in two significant figures.
Okay, so I'm thinking we'd have to convert this to that whole number decimal format by changing that pi to 3.14.
3.14 and multiplying that
Yes.
1,296 by 3.14 would give us 4,000.
4,096.44 cubic centimeters.
Right, 69, right. And that
69,
is,
yes.
we needed two significant figures. So remember in previous lessons,
We did significant figures in previous lessons.
Yeah, so how many significant figures we have now on the board?
Oh, we have a lot.
So if we count them,
We'd have all of them. So 1, 2, 3, 4, 5, 6.
6, okay. All right, and we need 2.
And we need 2.
So when we do our rounding off,
We would get
4,000.
4,100 cubic centimeters.
all right, we have to go on. This one is interesting, Tyrone.
Yes, it is.
It looks totally different from the ones that we've been looking at before.
Yes, it's not combined, but it seems to. Let's see.
Yeah, let's see.
The diagram below, not drawn to scale, shows a 0.5 centimeter thick cardboard box containing a fragile cylindrical glass vase and tightly stuffed with packing paper for protection. The vase touches both faces of the box as shown below. And we want to find the maximum volume of the packing paper that is going to be required.
Okay, so this cylindrical shape in here is the vase.
Yes.
And we need to find the.
And we realize that cylindrical vase is kind of taking up some of the volume
Of the box.
Of the box. So
Yes.
what is going to be left
Yes.
is going to be the packing paper.
And the box, so the vase is cylindrical and the box is, we can see
Cuboid.
it's a cuboid. All right. So let's do some calculation.
So let's try to find the volume inside the box.
Okay.
Right? Before we start, they had said that the container, the box, it had a thickness of 0.5.
Okay.
Right?
Yes.
How would that affect our calculations, Nikisha?
Well, it means that we'd have to subtract this 0.5 from each of the dimension
Yes.
going around with our calculation.
Oh, okay.
All right, so it therefore means that looking at the box, or 10,
Yes. So if we're taking for the dimension, especially on this face,
Yes.
this rectangular face, if we're taking half of centimeter on each side, we're left with 9 for that dimension and
14
yes.
for the other dimension. And working with what we have, area of cross-section times the height would give us a volume of 1,134 cubic centimeters. So let's look at the volume of the cylinder.
Okay.
It has a diameter of 5 centimeters and a height.
Okay. And we had already calculated the height to be 14
Right.
when we did that calculation before.
Right.
But what we needed to find was the radius, which is going to be half of the diameter. And the
2.5.
diameter is 5, so it's going to be 2.5.
All right. So we're coming on nicely.
So in this situation, as we had said before, we have some space within the box, right? The cylinder is obviously taking up some of that space.
Yes.
And the packing paper would be the volume or the space remaining in the
Right.
box.
So in this case, would we add?
No, I'm not thinking because the cylinder is taking out some of the space.
Right,
Right.
right. So we have to be careful when we read our question to know where it's not all the time we're going to be adding. Sometimes we'll need to subtract, but we still maintain to find the volume, working with the volume of the different
And we
components.
decomposed, yes.
Yes. So therefore, when we do our subtraction, when we find the difference between the two solids, we realize that the maximum volume of packing paper would be 859 cubic centimeters.
Okay, let us look at this one. This looks very familiar. Okay, so let us look at it. A solid shape is composed of a cylinder with a hemispherical base and a conical top, as shown in the diagram. Calculate the volume of the shape. And we're giving our answers in two significant figures.
All right, so we have three parts here. So when we decompose this compound solid, we have a cone, cylinder, and a hemisphere. And we know how to find the volume of each part.
Yes.
So far, we have been looking at.
And we're realizing that the diameter of 6
Yes,
for the hemisphere
yes,
is going to be the same diameter
for the
cone.
cone. Awesome.
Right.
So therefore, mean the radius would be 3.
Yes.
As the radius is half of the diameter. Substituting those values into the formula for volume of a cone, we get the volume,
To be 27 pi cubic centimeters.
So let's look at the cylinder.
Okay, we're going to use the same radius
Yes.
and substitute it into the formula, and that will give us the total volume of the cylinder to be 180 pi cubic centimeters.
And remember, the hemisphere would be 2/3 the pi r cubed. So substituting 3 again for our radius in our formula, we would get the volume of the hemisphere to be 18 pi cubic centimeters. And we want the total volume, so we would
add in this case because these regions are added together and not being removed from each other as in the previous case.
We need our answer to be in significant figures, so it therefore means that we would have to
multiply that 225
by
by
pi,
3.14, which is pi, and we'll get 706.5
cubic centimeters. So on the board we have 4 significant figures and we need 2. So when we do our rounding, we would get
710 cubic centimeters.
good. Another example. Now we would know exactly what to do with this one. So let's look at something that is another one that's a little bit different. Here, CSEC question.
Wow, this is interesting. So let's see what the question says. The diagram not drawn to scale shows an open cylindrical container made of metal and a circular base, and it has a uniform thickness throughout. And they're asking us to use pi as 22 divided by 7.
Awesome. All right.
We're asked to determine
the volume
of the metal that is used to make the container.
So let's decompose.
Yes.
So the outer cylinder.
The outer cylinder is going to have a radius as highlighted there as 15 centimeters.
All right, so substitute 15 centimeters as a radius into the formula for volume of cylinder.
And the height would have been 120.
And we'd get a volume of 84,857 cubic centimeters.
Yes.
Let us look at the volume of the inner cylinder.
This is where the analysis takes a little bit more time.
Yes.
We know that the radius of the inner cylinder is 14, that was given.
Yes.
What we have to determine is the height because obviously the inner cylinder doesn't go all the way down.
Right, right.
So in this case, we have to determine what that height is going to be. It's going to be less than the 120.
It would be less than 120 as the inner cylinder stops here.
Yes, but they had mentioned that it had a uniform thickness throughout, and we realized that this cross-section was for the inner cylinder had a radius 1 centimeter less than the outer cylinder.
Yes, yes.
So if it had a uniform cross-section throughout, the height would also have to be 1 centimeter less.
And that's how we get the 119 for the height of the inner cylinder. Substituting those values using radius to be 14 centimeters, we get a volume of 73,304 cubic centimeters. Yes. So, the volume of the material needed?
Well, I'm thinking in this case, we're taking out the inner cylinder in order to find what is left for the material. Right?
So it therefore means we wouldn't...
We wouldn't be adding in this case, so it would have to be a subtraction.
All right, so when we subtract the two volume here, we get a difference of 11,553 cubic centimeters. Okay? And I think that's, let's look at another CSEC question.
Okay.
And this is a question.
The diagram, not drawn to scale, shows a box with no lid. The sides and the bottom of the box are 1.5 centimeter thick. Calculate the volume of the material used to make the box. It's similar to the one that we just did.
Yes, very similar. So, taking into consideration, we'd have to find the volume of the outer cuboid. And remember, the volume of the rectangle, we're looking at the cross-sectional area, would be a rectangle times the height.
Yes.
So that's how we'd have length times width times height, substituting, and give us a volume of 9,000 cubic centimeters. The inner cuboid?
The inner cuboid, we have some considerations to make in this situation.
Yes.
Right, so they had already told us that the box had a thickness, right? There was no lid, firstly.
Yes.
So we know that this region that is 15, right?
Yes.
We would take 1.5 from it on the base.
The base
of it.
Yes.
But there was no lid, so we wouldn't need to take it from the top.
Okay.
Right? So that would be 13.5 for that height. And then from the other regions, we would just subtract the 1.3 on both sides. So that would be 17 centimeters. That 20 would change to 17. And that 30 would change to 27.
Okay, awesome. So that information of the 1.5 centimeter thickness is crucial to our values that we're going to plug into our formula to find the volume of the inner cuboid.
Yes.
And as you said, remember we didn't have the lid.
We didn't have any lid, so we only needed to take it once.
Okay.
For the height.
Okay. Now, when we substitute those values, we would get, as Tyrone did, with what 13.5, 17, and 27. So our dimensions reduced. And when we multiply them, we get a volume of 6,196.5 cubic centimeters. We're adding or we're subtracting?
Again, as we did before, it is going to be, they're asking us for the material, so it's going to be what is left after we take out that inner region.
Yes.
So that would be a subtraction.
That would be a subtraction, yes. So it's very important that we pay attention to what the question is asking, what is given in the question, and to take into consideration the different information that we have and how it will affect the dimensions of the solids.
Yes.
So after subtraction, we would get a volume of 2,803.5 cubic centimeters. Now here's another example. We have a cylinder.
That's a familiar one.
Yes. We have a cylinder and a hemisphere.
Yes.
You remember what is the formula for the volume of the hemisphere out of your head?
I'm thinking it's going to be a half, so it's going to be 2/3.
Yes.
Okay, we'll leave this question for now. We're going to our final break. We'll wrap up when we return. Stay with us.
Welcome back. Let's continue.
Okay, Nikisha, so let us do a quick recap. So,
Yes.
so far we would have been looking at the volume of compound shapes.
Yes.
And we would have done a recap on how it is we find the volume of different types of shape. Can we do a quick recap in regards to how it is we find the volume of a prism and a pyramid and all of these different shapes that we'll be utilizing?
Okay, so based on our exploration, we realized that if we take the area of the cross-section, a uniform cross-section,
Yes.
and multiply that by the height, we will get the volume of the
Prisms.
prisms.
Okay.
We also explored where we realized that the pyramids are 1/3 the volume.
The volume of the prisms.
Yes, the pyramids are 1/3 the volume of the prisms.
Yes.
And an interesting one was the sphere.
And that's important for us to recall. So let's repeat that. The volume of the pyramid is 1/3 the volume of the associated prism.
Yes. So for example, the cone.
Yes. And the association is when it has the same height
And diameter.
diameter
in
or cross-sectional area.
Yes. So
At the base.
for the cone, the associated prism would be the
Cylinder.
cylinder. All right. And for the square base pyramid,
It would be a rectangular prism.
would be a rectangular pyramid. So we realized that those would be, the volume of the cone would be 1/3 that of its associated prism.
And we also found that when we are finding the volume of composite solids, we can do a number of things.
Yes.
If it is that they are regions are being combined together, we can first identify the individual shapes.
Yes.
Then we find the volume of each individual shape, and
Yes.
then we make the decision as to whether we're going to be adding or subtracting those volumes to get the final solution.
Yes, very important. And also, based on the questions that we have been working, we realize that we also have to pay attention to the information that is given in the question.
Yes.
And so that will be a deciding factor on the size of our dimensions, whether they're going to change by increasing or decreasing
or
through
they'll remain the
subtraction,
same.
or they will remain the same.
Okay, let us look at this question. The diagram below shows a design of a water tank. The water tank consists of a cylinder capped with a hemispherical dome. Find the capacity of the water tank, and we're giving our answer in liters this time to two
Okay.
significant figures.
And notice our dimensions are in meters.
Yes.
All right. So let's see how this turns out.
So as we would have done before, we're going to be decomposing and finding the volume of each region. So we'll start with the hemisphere.
Okay, when the formula would be 2/3 pi r cubed. So notice that our diameter of the circle is 6 meters. So it therefore means the radius would be
It would be 3 for the radius.
half of 6, which would give us 3. Substituting that 3 into our formula, we'll get a volume or the capacity.
Of 18 pi cubic meters.
Awesome. So we have looked at the hemisphere. Let's look at the cylinder.
We're also using the same radius for the cylinder. So it is going to be 45 pi cubic meters.
Okay. So therefore, the total capacity for this cylinder-capped water tank is...
It's two shapes being combined together. So we're going to be adding them to get 63 pi cubic meters.
Cubic meters.
Yes.
Ooh.
Oh, okay. You jumped ahead a little bit.
No, we're going
Back.
Going back.
Okay. So we have cubic meters.
Yes.
But the question is asking that we give our values in liters.
Yes.
So we have to find a way to convert this cubic meters to cubic centimeters.
And the relationship between the meter and the centimeter?
I can recall that 100 centimeters gives us 1 meter.
You're right.
So that would be for one dimension. So let us see how that will affect the volume of a cubic
Would we need...
meter.
All right, okay.
Here we can see if each dimension is 100 centimeters, right?
The volume.
Right, so this was originally one meter by multiplied by 1 meter multiplied by 1 meter. And we changed those values, those 1 meter to centimeters, which is 100 centimeters each.
Right, okay.
And when we do the multiplication, we get 1 million
Cubic
centimeters to be the equivalent to 1 cubic meter.
Yes, yes. So bearing that in mind, we'll convert that 63 pi cubic meters to centimeters.
Yes, and by multiplying by that 1 million being our new conversion rate from cubic meters to cubic centimeters.
Awesome. So it's now in cubic centimeters, and we are to give it in liters. So we're not there yet.
We're not there yet.
Okay.
We can also recall, based on our knowledge of liters, when we had discussed it in primary school, that 1,000 cubic centimeters gives us 1 liter.
Yes. So this is what we're saying. So no, therefore we need to change this cubic 63 million pi cubic centimeters to liter.
To liters, and we divide it, and we get.
We would divide that by
1,000.
1,000, and we'd get
63,000 pi liters.
All right. So notice that we're asked to give it 2 significant figures, and seeing that pi is not yet. We haven't applied pi.
Yes. So we'll multiply that 63,000 by 3.14 as we had done previously. And we will get that to be 197,820 liters.
820 liters. Good. And we have there 6 significant figures. 6.
Yeah.
And we need 2.
Yes. So we have to round this off, and we will get 200,000 liters when we convert that.
Right.
And we round it off to 2 significant figures.
Okay. Awesome. So that one was very interesting as we were changing from cubic meters, we changed to centimeters, and then we also changed to liters.
So this took a lot of work.
Yes.
So it's just following it step by step.
And applying all the knowledge
we had
before. So let us look at the summary of what we did today. So we know that the volume of compound solids can be found by adding or subtracting the value of their individual parts.
We can visually determine if each region is going to be removed, which is subtraction, or going to be combined with it, which is going to be addition.
Awesome. And if the compound solid is a prism, we can apply the volume formula for prisms as an alternative.
And finally, the volume of a prism, this is important, the volume of a prism is the cross-sectional area multiplied by the height.
Awesome.
Unfortunately, that's all the time we have for this lesson, but you can keep practicing on your own at home until next time. Stay safe.
Hi there, I'm Simon Preston from TVJ. Thank you very much for watching our YouTube channel. To see our latest videos and also to see live events, click here. To see our full videos on onespotmedia.com, click here. Thank you very much for watching.